In this lecture, we are going to define the Lie bracket of two vector fields. Moreover, we will define the Lie derivative of one vector field by another. And these two concepts, we are going to show that they coincide. The Lie bracket of two vector fields is equal to the Lie derivative. The equivalence is going to be useful to show that the local flows of two vector fields commute if and only if the Lie bracket is equal to 0. We are also going to see some rectification theorems for either a vector field that is non-singular in a neighborhood of a point, or a finite family of vector fields that are linearly independent at a point and commute. And moreover, we will see that the space of C-infinity vector fields on a manifold has the structure of a Lie algebra. And indeed, we will introduce the properties that define a Lie algebra. So first of all, we are going to consider coordinate changes for vector fields. So consider X as infinity vector field defined on a manifold M, and Y as infinity vector field defined on N, and then a map, as infinity map from M to N. We say that X and Y are related if the differential of f at the point small x sends the vector, the tangent vector given by the vector field capital X at the point small x to the tangent vector defined by y at the point f of x, and that for every x. So the differential is sending the vector field x to the vector field y. In particular, that's going to imply that f sends trajectories of capital X to trajectories of capital Y, okay? Of course, if f is a diffeomorphism and we fix a capital X, there exists a unique vector field capital Y such that X and Y are f related. Indeed, we can use this formula to define capital Y, okay? But this definition, being f related, can actually be considered in situations in which f is not a diffeomorphism, not even a local diffeomorphism, okay? So when we have two vector fields, x and y, that are f related, we consider the local flows of x and y that we are going to denote by phi t and psi t respectively, okay, and we get this formula. The composition of phi t with f is going to be the composition of f with psi t. And the reason is that f sends trajectories of x into trajectories of y. If we consider a point C in M, okay, when we consider this curve parameterized by t, this is a trajectory of the vector field x. So if we apply f, okay, and we consider then this other curve, this has to be a trajectory of the vector field y. And so it has to be psi t applied to the initial condition. Okay, but the initial condition is obtained with when t is equal 0. Phi 0 is the identity, so this is when t is 0 is f of c. So we have this expression that holds for t, and as a consequence, the composition of phi t with f is going to be equal to the composition of f with psi t for a small t, because the local flows are not defined in general for every t. But we have this very interesting property. Now, we can use this property to calculate, given a C-infinity function defined on n, y applied to h, and then compose with f, pre-compose with f at a point x. How do we do this? Okay, this y applied to h at some point, which in this case is f of x, is the derivative of psi t composed with h applied to the point f of x with respect to t and evaluated at 0, right? But now we can actually use that this composition over here is equal to the composition of phi t and f, and we get this. And this is just the definition of the value of x applied to f composed with h in the point x. So since this holds for every point x in our manifold, we get that x applied to f composed with h, this is a C-infinity function of m, and so this, because x is the derivation of the space of C-infinity functions of m, is also a C-infinity function of m. This is a C-infinity function of n, but when we compose with f, it's a C-infinity function of m. These two C-infinity functions of m, we prove that indeed they are equal. So we have this expression. This expression holds whenever we have that two vector fields are related. And indeed, if this expression holds for every h, then the vector fields are f-related. Before introducing the Lie bracket, we're going to consider the following theorem, which is an auxiliary theorem. So consider a vector field. This is a rectification theorem because it says that in the neighborhood of a regular point for a vector field, then our vector field up to a change of coordinates is a coordinate vector field. We can consider a local chart such that the local chart relates x with this coordinate vector field, okay? And first of all, this is a local theorem, so up to consider a local chart, we can consider that m is equal to Rn, and our point x0 is just the origin, right? And now we can write down the expression for our vector field. Okay. And what happens is that one of these coefficients is different than 0 at the point 0. Let us assume that is the first one. Okay, suppose that a1 of 0 is different than 0. Now we're going to consider a map which is defined from R times Rn minus 1. Indeed, it's going to be defined in a neighborhood of the origin to Rn, and that sends the point x1, x2, and so on to the flow in time x1 applied to the point 0, x2, and so on. Okay, what happens now is that, okay, here it was. So what happens is if we consider x1 equals 0, all the points in that hyperplane are going to be fixed by our map f, and the point x1, x2, xn is sent to the result of following the flow of the vector field x at time equal to x1 when the initial condition is 0, x2, x3, and so on. Okay, what happens if we consider the differential of this map at 0? It is defined when x is in a neighborhood of 0, okay, because of the properties of ordinary differential equations. And this differential of f at 0 is going to be clearly a matrix that has the following properties. We have to realize that when x1 is 0, this is just a map that sends x1, x2, and so on to 0, x2, x3, and so on. So this implies that the second line of our differential is going to be equal to the second line of the identity matrix. The third line is going to be equal to the third line of the identity matrix, and so on. And the first line is going to be just the expression of the vector field at 0. Okay, so it's going to be A1, A2, and so on at 0. What happens is that clearly this matrix over here is invertible if and only if A1 at 0 is different than 0, okay? And but we assume that, so this differential is an invertible matrix. This is an isomorphism of Rn, and as a consequence, we can apply the inverse function theorem. And that implies that there exists an open neighborhood W of the origin in Rn such that f defined in W and that goes to f of W is indeed a diffeomorphism, a C-infinity diffeomorphism. Something that it is interesting is that this capital F relates the first coordinate vector field, because if we fix every xj except the first one, this parameterizes a trajectory of this vector field. But if we fix all the xj's with j greater or equal than 2, this parameterizes a trajectory of x. So capital F relates the first coordinate vector field and x. So it's a change of coordinates that sends the first coordinate vector field to x. If we consider the inverse of capital F, this is going to relate our vector field x with the first coordinate vector field. And so we this completes the proof, okay? Now we are going to define, finally, the Lie bracket and also the Lie derivative. So consider two vector fields, x and y, C-infinity vector fields, and we are going to define the Lie derivative of y by x as this expression. It's going to be a vector field that at the point C is the limit of this expression over here when t tends to 0. Okay, we can consider actually a map TC that sends this, a map that sends TC to this expression. And what happens is that the Lie derivative is the derivative with respect to t at t equals 0. Since this expression over here is C-infinity in the variables t and c, this Lie derivative is a C-infinity vector field, okay? We can also define the so-called Lie bracket of two vector fields, x and y. we have already seen that there is an identification between vector fields, C-infinity vector fields, and derivations of the space of C-infinity functions. So it suffices to say how the Lie bracket behaves as a derivation. So consider a C-infinity function f. We're going to define the Lie bracket of x and y as the map from C-infinity functions to C-infinity functions that sends f in this function over here, x applied to y of f minus y applied to x of f. Okay? Something that we can notice is that obviously xy is a map from C-infinity functions to C-infinity functions, and it's obviously are linear because x and y are linear. But what it is not completely obvious is that it is a derivation. This is just some calculation, okay? I'm going to let that exercise to you. What you have to show is that with our definition, the Lie bracket of x and y applied to a product of two functions is equal to the Lie bracket of x and y applied to f times g plus f times the Lie bracket applied to g. And it is easy to see that this property holds. And so because of that, the Lie bracket of two derivations is going to be a derivation. And by using the identification between C-infinity vector fields and derivations of the space of C-infinity functions, we get the definition of the Lie bracket of two vector fields, okay? The Lie bracket satisfies the following properties. The first one is that it's are bilinear, okay? This is obvious from the definition. Then we have this one, which is also obvious from the definition. The Lie bracket of x and y is antisymmetric, the Lie bracket is antisymmetric, so the Lie bracket of x and y is minus the Lie bracket of y and x. Okay, and finally, we have this identity, which is called the Jacobi identity that we can check out directly. And that says that the Lie bracket of x and the Lie bracket of x with yc, with the Lie bracket of y and c, plus the Lie bracket of c and the Lie bracket of x and y, plus the Lie bracket of y and the Lie bracket of c and x, sum of all these Lie brackets is going to be equal to 0, okay? And indeed, if we have R bilinear operation defined in a vector space B that satisfies the previous conditions, so in particular it is antisymmetric and it satisfies the Jacobi identity, then we say that B is a Lie algebra. Indeed, a Lie algebra over R, okay? So in particular, what we get is that the space of C-infinity vector fields is a Lie algebra, okay? Now we want to show that the Lie bracket and the Lie derivative coincide, okay? So we can check out that these two vector fields coincide at every point. First, consider C a point of M that does not belong to the singular set of the vector field X. Okay, since the definitions of these two objects are local, we can work in local coordinates. And so by the rectification theorem, we can suppose that our manifold M is actually Rn for some n, and that our point C is the origin, okay? Very good. Indeed, by doing another by doing the change of coordinates that is provided by the rectification theorem, we can suppose that x is the first coordinate vector field. Okay, and now we want to calculate this Lie derivative of y by x. It's going to be the derivative with respect to t at 0. Okay, and here we have the differential at the point phi sub t of w of phi minus t applied to y of phi t double. Okay, and this is at t equals 0. The issue is that since our vector field is just the first coordinate vector field, phi t of x1, x2, xn is just x1 plus t, x2, and so on. So this map for every t is a translation, and the differential of a translation is the identity. So what we get is that this expression is going to be just this one. Okay, it's going to be the derivative with respect to t at t equals 0 of y of phi t of w. Okay, but if we have, okay, so this is the expression that we found. Very good. But y at the point phi sub t of w is going to be just the sum if y, okay, let's express what's y. Y, it's going to be the sum of aj times partial with respect to xj, and y at phi sub t of w is going to be the sum of aj. Okay, and let's consider here x, which is going to be simpler. Okay, and here x again, and this is going to be x1 plus t, x2, and so on, times the derivative with respect to xj. If now we derivate this with respect to t and evaluate at t equals 0, what we get is that the Lie derivative of y by x at a point small x is going to be just the sum from j equal 1 to n of the partial derivative of a j with respect to x1 at the point x times the partial derivative with respect to xj. Very good. So we have this expression. And now we can calculate too the Lie bracket of x and y, knowing full well that x is just the first coordinate vector field. And if we apply this to some xk, what happens is that this is going to be the partial with respect to x1 of y applied to xk, that's just ak, right? Minus the result of applying y to the partial of xk with respect to x1. That's going to be 1 or 0. And y applied to any constant is always 0. So we don't have to consider anything else. And as a consequence, the Lie bracket of x and y is going to be the sum from j equal 1 to n of the derivative of a sub j with respect to x1 times the corresponding partial derivative. But then it's clear that these two expressions are equal, so the Lie bracket of x and y is equal to the Lie derivative of y by x. Okay? And something that it is interesting is that if C satisfies that is a singular point of x is an interior point of the singular set, then it is very, very simple to show that this Lie derivative at the point C is equal to 0, okay? And also that the Lie bracket at C is equal to 0. So these two objects coincide. So they coincide in the singular set, in the complement of the singular set, and they coincide in the interior of the singular set. But now we realize that we have this equality in a dense set, because the union of the set of regular points and the interior of the set of singular points is dense. And so as a consequence, we get that the Lie derivative of y by x coincides with the Lie bracket of x and y, as we wanted to prove. In this lecture, we defined the Lie bracket and the Lie derivative associated to two vector fields, and indeed we proved that they coincide. In our next lecture, we are going to see a geometric consequence of such a property. Indeed, we will see that the local flows of two vector fields commute if and only if its Lie bracket is equal to 0. Thank you for your attention.